So the next presentation, it will be the influence of the grain size on cleavage crack propagation resistance in ferritic steels. Yuta Suzuki.
Thank you, Chairman. I'm Yuta Suzuki from the University of Tokyo, and I'd like to talk about the influence of grain size on cleavage crack propagation resistance in ferritic steel. And here is the outline of my presentation. First, I introduce the issues. Cleavage crack propagation in steels occurs suddenly and at high speed, and has a risk of giving structures crucial damage. Thus, it is a phenomenon to be prevented absolutely. And it is required to improve not only cleavage crack initiation toughness, but also crack arrestability. And in recent study, for improvement of brittle crack arrestability, we should make cleavage crack propagation resistance high. There are two types of cleavage crack propagation in BCC solids. One is cleavage plane, and the other is tearage. Cleavage planes are formed on 100 plane of grains. And tearage is a ductile fractured ligament between two cleavage planes along grain boundaries. And we focused on tearages. Because of the viewpoint of effective surface energy, that is energy dissipation because of formation of cleavage crack surface, and plastic work in forming tearage is the most dominant factor. It is well known that microstructures make a substantial contribution to material resistance to cleavage fracture. For example, the relation of grain size and brittle fracture initiation toughness is well known. However, effect of grain size on cleavage crack propagation resistance is not clear, even though it is one of most fundamental features of steels. So, our objective is to clarify the significance of grain size on cleavage crack propagation resistance. To do it, we investigated the effect of grain size experimentally and calculated absorbed energy during cleavage crack propagation by numerical model using XFEM, presented by Shibanuma et al. In previous section. Next, I'll explain crack arrest tests and the methods of estimation of cleavage crack propagation resistance. To begin with, local fracture stress is employed as the representative of cleavage crack propagation resistance. It is a material constant independent from temperature and applied stress. And as follows. And it is I show you the procedure to evaluate grain size dependency. First, I prepared steels whose grain size is only different. And second, we carried out small crack arrest tests in various temperature conditions. Third, we calculated local fracture stress by finite element analysis. Finally, we evaluated cleavage crack propagation resistance. In other words, we compared local fracture stress for steels with different grain size. We prepared three types of ferritic steels. upper half a picture of optical observation of microstructures of steels. Sigma y is yield stress. And the lower half are the polar figures. As shown from these figures, these still look isotropic. Chemical compositions are almost the same. From this grain size distribution by EBSD, average grain size approximately from 15 to 55 micrometers. Grain size of S1 is the smallest, and that of S3 is the biggest. We carried out DCB type tests for small crack arrest tests. They required low cost to be conducted, so we conducted many times in various temperature conditions, and they were low SIF tests. So we could reduce macroscopic fracture surface roughness. Other factors were excluded as long as possible, because this study aims to evaluate the resistance due to grain size. In TCB tests, static loading leads brittle fracture, so it is easy to represent experimental results by FEM. And these specimens have high arrestability. And we made chevron notch in these specimens to make crack generate easily. And in brittle crack propagation, displacement is fixed too. Totally 8 experimental results were obtained. Cleavage fracture surface were obtained by breaking ligaments after crack arrest. However, it is hard to distinguish crack arrest points, so heat tint was employed after crack arrest to color cleavage surface and in practice. We measured crack arrest lengths after heat tint. In general, the cracks were arrested in shorter lengths in coarser grain steels. After we obtained experimental results, we conducted finite element analysis. We carried out 3D elastoplastic dynamic implicit analysis using Abacus 6.14. And in this model, we considered quarter model symmetry and crack front shape straight. And minimum mesh size is 0.1 millimeter, and characteristic distance was set to 0.15 millimeter. We conducted dynamic crack propagation analysis using nodal force release technique and evaluate maximum principal stress at characteristic distance from the crack tip. This movie shows finite element analysis results. At first, pin force displacement was imposed to rigid pin. Until displacement reached experimental results. And once it reached experimental results, crack propagation started. In this movie, we assumed the crack velocity 300 meters per second. The crack velocity just before the crack arrest is considered to be from 100 to 300 meters per second at low temperature. So to estimate local fracture stress, firstly, we plotted local tensile stresses in the case that and the crack velocity is 100, 200, 300 meters per second. And the local fracture stress is independent from the crack velocity. So when the tensile stress is at each crack velocity cannot satisfy local fracture stress and crack arrest. So at the arrest length obtained experiments, at the crack arrest length obtained by experiments, the maximum local tensile stress estimated by finite element analysis in the three types of finite element analysis results. The maximum is the local fracture stress. The result of estimation of local fracture stress for each steel is this graph. Although there are some scatters, the estimated local fracture stresses were almost constant for each steel. The estimated local fracture stresses are totally higher in coarser grain steels than in finer grain steels.
2 minutes, please.
Okay, thank you. We calculated absorbed energy during cleavage crack propagation. Procedure is this. First, we prepared grain distribution and calculated cleavage crack propagation presented by Shibanuma et al. In previous section. And we simulated to form cleavage and evaluated absorbed energy. We used this model presented by Shibanuma in previous section. And energy for cleavage formation is much bigger than energy for cleavage fracture plane. So it is we had better only cleavage. And absorbed energy is this expression derived by Shibanuma et al. We used this expression. And cleavage, we explained the method of cleavage formation. And we don't have enough time, so this. This black part is cleavage. And this is input data to simulate grain distribution by Nepal. And the result of the absorbed energy is this. And we compared simulation results and experimental results. And both results have the trend that the absorbed energy increases in proportion to grain size. In conclusion, we tried to investigate the effect of grain size on cleavage crack propagation and resistance, experimentally and theoretically. And it is shown that coarser grain has higher cleavage crack propagation resistance. Thank you for your kind attention.
Thank you very much.